So I thought it was time I tackled last year's Extension 2 exam, and I'm not sure how many questions I'm going to do, but I'll work backwards from the end. So today I'll do question 16. So I'm not sure if I'll do all of them, but if there's a particular question that you want me to go through, then just let me know in the comments. Okay, so for this first one, what I would do first is sub this into here. And then the idea is that we want to, simplify that, mess around with it, and show that it's equal to 0. So you don't want to start by assuming it's 0. You just want to start by writing that down and simplifying it, because you don't want to assume what you're trying to prove. Okay, so what can we do with that? Well, what I would do is look at this, and we could actually think of this, because it's going to be kind of messy with the square roots if we try to just sub that in directly. What I would do is just think of this as r squared being 4p on 3, and then maybe we can think of this as being r squared times r, and then just replace the r squared. So we're going to get that. I mean, you could replace all the r's, but it's just going to be annoyingly messy. So what we would like is to be able to use this. So I'm sort of looking at this and thinking, like, maybe we can factorize that, and it's going to end up with that. So let's give that a go. So we've got a factor of PR in both of these things, and let's also pull the 3 out the front. And then that's great, because then we're left with this. So that is cos 3 theta. So we can replace that. And then also we know that cos 3 theta is negative 4q on r cubed, so that's what that is. So we've got PR on 3 times negative 4q on r cubed. And then we just need to simplify this, so that will cancel with one of those. So we've got that on 3r squared, and then I might use this again. And then we can cancel a lot of stuff here. And we get negative q plus q, which is 0. So that's it for part 1. So that's showed that is a root of that. Okay, so for part 2, now the easiest way to do this one would just be to reason that if alpha, beta, and gamma are roots of this, then if I turn it into x minus 3, if I replace all the x's with x minus 3, then alpha plus 3 and beta plus 3 and gamma plus 3 are going to be roots of that equation, because if I plug in alpha plus 3 sub x equals alpha plus 3 into here, then you're just going to have alpha cubed plus 9 alpha squared and so on, and we know that that's 0 because alpha is a root of this. So we just need to expand this and show that it's the same as that. Now if you forget how to expand this, it's just binomial theorem. So let's just revise that. It comes out like that. So that will make x cubed, and then we've got 3 times the x squared times the negative 3, so negative 9x squared. And then we've got 3 times the x times the negative 3 squared, so that'll be positive 9, and then times 3 at 27. And then the negative 3 cubed, so minus 27. Okay, so that's that bit, and then we'll have 9x squared, and then it's going to be minus 6x times the 9 is negative 54x, and then plus 9 times the 9 is plus 81. I'm running out of space. Okay, and then we just need to simplify that. So we've got x cubed, that cancels with that. We've got 27x minus 54x plus 15x. So that will make, that's negative 27 together, and then that makes negative 12. And then we've got negative 27 plus 81 minus 45 minus 17, which does in fact make minus 8. You can do that on your calculator if you don't want to do all those by hand. Yeah, so then that's pretty much it. That's that proves that those are roots of that. Okay, now for part 3, the idea with this is that we can use all of this to solve a cubic equation that doesn't have an x squared term. If we want to solve one that does have an x squared term like this one, then we have to use a transformation like this to sort of transform this into this. So we've just sort of shown that this is equivalent to this as long as we do this little shift of the roots. So if we can solve this one, then we can just subtract 3 from each of the roots and we'll have the roots of this equation. So we just need to use all this to solve this equation. So we've got, that's the p, so p is 12, and then the q is negative 8. So we just need to apply these formulae. So r will be root 4 times 12 over 3, that makes 4. And then we've got cos 3 theta is negative 4 times the negative 8, so that's 32, on r cubed, which is 64, so 32 on 64, which is a half. So the roots of this equation will be of the form r cos theta, and there's going to be multiple solutions for theta, so that's why we have 3 roots for that. So we're going to have to work out what theta is. So I'll use the methods that I was explaining in my series on trig equations, so I'll put a link to that up here. So we want to solve for 3 theta, and I'm going to do it in like general form. So you've got 2n pi plus or minus that angle, which is pi on 3. I think doing it in general form is usually easier for this kind of question. And then we just want to move the 3 over the other side. So we've got 2 pi on 3 times n plus or minus pi on 9. Now let's just visualize where all those solutions are. So when n is 0, you'll just have plus or minus pi on 9, like that. When n is 1, you'll have 2 pi on 3, which is around here, and then plus or minus pi on 9, so like there and there. And then when n is 2, we've got 4 pi on 3, which is like down there, and plus or minus pi on 9, so it's like there and there. So there's actually 6 solutions, but the thing is, because this is using cos theta, it's like that one has the same cosine as that one, so like that solution's kind of redundant, and that angle has the same cosine as that angle, and so on. So we really only need to consider the first 3 solutions. So we could say theta is, that one will be pi on 9, that one is 2 pi on 3 minus pi on 9, which is 5 pi on 9, and then that one is 7 pi on 9. So then we can just say, so the roots are going to be, so r cos theta where r was 4. So the first root would be 4 cos pi on 9, and then we have to subtract 3 because of this transformation. Like, that by itself is the root of this equation. If we want the root of this equation, then we got to subtract 3 from it. Because the 4 cos pi on 9, that by itself is like alpha plus 3. So subtract 3 to find alpha. So yeah, and then the rest are just those other angles. Like that, and like there's no simplification we can do with, you know, cos pi on 9 and so on. So we just leave them like that. Okay, part B. So what I would do here is I like to write out that if these are the roots of p of z, then you can factorize z like this. Now maybe you've memorized how to get these coefficients from the roots, but I tend to not memorize that. I just write it out like this and then figure them out. So what we could do is look at this coefficient in the z cubed, for instance. How does that come from expanding this? Well, for example, you would have like negative alpha times z, z, z. So a negative alpha z cubed, and likewise you'd have a negative alpha bar z cubed, and so on. So we could say that 2k is going to be alpha plus alpha bar plus beta bar. And then just a bit of a revision with complex conjugates and things. So if alpha was x plus iy, then alpha bar would be x minus iy. So if you're adding those two together, then those cancel and you end up with 2 times the real part. So this is 2 times the real part of alpha, and likewise this is 2 times the real part of beta. And then we could divide both sides by 2, just to clean that up a bit. Okay, so that's cool. Doing stuff to these coefficients doesn't get us anywhere. I did try that. But this is the other important one, so let's work out how that comes from these roots. So that's the coefficient of the z squared. So for example, you would have like negative alpha times negative alpha bar times z. That would be one of the z squared terms. So that gives you alpha bar. Yeah, and then all the other products as well. So alpha beta and alpha beta bar and alpha bar beta and alpha bar beta bar and beta bar. Okay, what can we do with that? Well, alpha times alpha bar is the same as the argument. No, sorry, I mean the modulus of alpha. So that's going to be 1, and that's going to be 1 as well. So those add up to 2. And then what can we do with this? Well, this to me looks like we can factorize that. Like with this, I could pull out an alpha. And then this, we can pull out an alpha bar. And then that's great because we've got this repeat of the beta plus beta bar, so we can factorize that even more. And then again, this is 2 times the real part of alpha, and that's 2 times the real part of beta. So we get 4 real part of alpha times real part of beta. And then that was 2k squared, so let's divide both sides by 2. And then what we could do is use this equation that we found before. We can sub that into there. So real part of alpha plus real part of beta squared we know that equals 1 plus 2. Real part of alpha, real part of beta. So we could expand that. And then we can cancel that from both sides. And then that gives us what we wanted. Okay, so that's part 1 done. Now for part 2. Let's think about that. So we know that the modulus of beta is 1, so that means it's going to lie on this circle. And now we know that this is true as well. So the way that I would think about it is like, if you imagine a little triangle there, this side is the real part of alpha, and this side is the imaginary part of alpha. And we know that, you know, they satisfy Pythagoras' theorem, so real part of alpha squared plus the imaginary part of alpha squared has to equal 1. So if you compare that to this, well, that tells us that the real part of beta will have to be plus or minus the imaginary part of alpha. So the real part of beta, its x-coordinate, is going to be the same as this, but positive or negative. So that would put it here, or here, or here, or here, where like each of those distances, each of those x-coordinates is the same as that. So those are the 4 possibilities. And just to sort of highlight, you know, how we got that, all these triangles, like that little triangle and that little triangle and so on, are going to be congruent with this one. So we could just say like all these angles are the same, like that angle is the same as that one, and that one, and that one, and that one. And then that's it for part B. Part C. So these geometry questions tend to be not too hard to understand the proof when you see it written out, but kind of hard to come up with. So what I would do with this kind of one is just try to think how we're going to use each piece of information we have, and like where the end result might come from. So one of the main facts that we have that we need to work out how to use is that all of these lie on a circle. So you might be wanting to use like angles standing on the same chord. There might also be facts about cyclic quadrilaterals, like these two are cyclic quadrilaterals. And then kind of like looking at where we want to go and working backwards from there. Well, this kind of reminds me of the sine rule. So I'm thinking we probably want to be doing sine rules in these triangles. So yeah, just try to like keep all of that in your mind. So you might start out maybe just in your rough working by writing down sine rules in these triangles to try to see how that's going to be relevant. Like it's going to be A on sine this angle equals E on sine this angle. And then in this triangle you've got D on sine of this angle is E on sine of this angle. And then how do we use that? And like where is the B plus E going to come from? That's sort of the main mystery in this as you're working through it, I think. So what occurred to me is that, so we've got like A on sine of this angle. So let's think about how this angle could be expressed as something to do with B and E, maybe. So I'm thinking this one is B minus this one. And then the way that E is going to be involved is that this is a cyclic quadrilateral, therefore that one plus that one has to add up to 180. So let's see what happens with that. Angle CBD is the angle B minus this one, which is because that plus that is 180, this is going to be 180 minus that. So, and then we can just simplify that. B plus E minus 180. And then we can do a similar thing with, we want something involving C plus E. So that's going to be using this relationship that plus that one is 180. And then that'll give us an expression for this angle. So I might just say similarly, angle BCA, that's going to come out as C plus E minus 180. And then let's see what we can make of that. So maybe I start with the statement of the sine rule in this triangle. So, oh, and I probably put some reason here about being a cyclic quadrilateral. Okay, so sine rule in this triangle. So A on sine angle CBD. Now we can't really do this side on this angle because, you know, that's not given a name or anything, so I guess I'll choose the E. I mean, you could, but it seems more obvious that E on this angle is going to be involved. Sine angle BDC. Now, how is that going to relate to the sine rule in this triangle? Well, in this one, we would have E on sine angle BAC. Now, BAC is actually equal to BDC because they're standing on that same arc, BC. Like that angle and that angle are going to be equal. So, BDC is the same as BAC. So you'd put an exclamation here about angles standing on the same arc, BC. And then, by the sine rule in this triangle, that's the same as D on its opposite angle, which is angle BCA. And the explanation here would be sine rule in triangle ABC. I should probably say something similar here. This is from the sine rule in triangle BDC. Okay, well, so now we've got that equals that. And now we can apply these things that we found. So this becomes A on sine B plus E minus 180. And this one was C plus E minus 180. Now, if you need a refresher on like trig identities, I did make a video on that, so you can check that out if you like. But this is going to be, this is the same as negative sine B plus E. And this one, that's the same as negative sine C plus E. So then we can just cancel the negatives, like multiply both sides by a -1, and we get that. So that's it for that one.